To your lesson on tree diagrams, independent, dependent events. This is lesson 2. It follows up on the same packet you were working on in class. You had one video lesson to get you started. This video lesson is intended to help you move on with the problem sets if you're having trouble with this, or just to check your work if you have done the homework and you want to see how you did on the first few. So here we go. First problem we're going to look at is the one with a bag containing 2 red, 1 green, 3 blue stones. You reach in, take 1 stone. Then you reach in again. Alright, reach in again, take another stone. Alright, scenario A. After drawing the first stone, you return it to the bag. So this is one of those situations where you do replacement, and that means the bag it gets reset to how it was in the beginning. So there's no change from the beginning. After drawing the second draw, there's no change. So are these independent or dependent events? These are independent because when you draw the first time and you draw the second time, the probabilities are all identical because you have reset the bag by replacing. So use the appropriate compound event to find the probability. So probability of a blue then red can be written as BR. Alright, so probability of blue and red, I'm using the equation that tells us this is an AND event, blue and red, and I'm going to multiply when it's AND. I'm just multiplying probability of the blue by red because there's no dependence here. So blue is 3 out of 6 stones, red is 2 out of 6. You multiply those two and you get 6 out of 36, which is 1 out of 36. 1 out of 30, 1 out of 6. That's your probability of drawing a blue and a red. Now let's go to the diagram on the bottom. Filling in the diagram, you have 2, 6, because that's a red. 2 out of 6 are red. Blue, the next one, first draw, 3 out of 6, and then 1 out of 6, because there's only 1 green out of 6. When you go to the next second draw, the probabilities remain exactly the same. 2, 6, 3, 6, 1, 6. 2, 6, 3, 6, 1, 6, 2, 6, 3, 6, 1, 6. And they're the same because, again, the stone has been replaced in the bag. So when you reach in that second time, you have exactly the same stones in there and your probabilities are the same of getting each stone. Make sure you understand that idea, the big idea. And finally, we need to find the probability on the bottom of red then green or green then red. So basically, what's the probability of getting a red or green stone in any order? So red or green would be probability of red-green. And since it's an OR problem, we're going to add those. Probability of red-green plus probability of green-red. Here are the 2 arrows to represent red then green. You follow the path to red and then follow to the end to green. So that's the red-green path. And now in blue, this is the green-red path. So you have to find the probability along each path and then add those 2 probabilities together. So the probability of red-green is 2, 6 times 1, 6. And the probability of green-red is 1, 6 times 2, 6. And I'm adding those 2 because it's an OR problem. So it becomes 2 over 36 plus 2 over 36, which is 4 over 36, reduces to 1 over 9. Make sure you got that right. If you tried it already, make sure you understand it. And now let's look at scenario B. In scenario B, we have a stone you've drawn, and now you have the same bag, but you do not return it to the bag. So let's see what happens. These events are dependent. These events are dependent because when you draw from the bag the second time, it is not replaced. So the bag contents have changed. And what you started with is different than what you have on the second draw. There's 1 less stone in there. So that probability formula is probability of red-green is probability of red times probability of green given that red has occurred. That just means that probability of green might be different than it was otherwise. So probability of red is 2 out of 6. Now a stone is gone, so there's only 5 stones left in the bag. And there's only 1 green stone left in there. So 1 out of 5 is your green given that red has occurred. It's a very important idea, dependence, make sure you understand. We have 2 over 30, which reduces to 1 over 15. So check your work. Now let's look at the tree diagram for that scenario. Here it is. Again, the initial probabilities are the same, 2, 6, 3, 6, 1, 6. However, now we've drawn 1 stone. So all the denominators will now be 5 because there's only 5 stones left in the bag. There's no replacement. So we have 1 out of 5. So notice how there's 2 6 and 1 over 5. 2 6 because there's 2 stones originally that were red, but now you drew a red stone and kept it. So now there's only one red stone left of the 5 remaining stones. The blue remains the same with 3, but it's over 5. And the green remains as with 1, but it's out of 5 as well. Now next time it's possibilities you draw a blue one. So now red is 2 out of 5. Blue has decreased from 3 to 2 blue stones, it's 2 out of 5. And green is still 1 out of 5. On the bottom you draw a green. So you've taken a green out. Now there's 0 greens left. So red is still 2 out of 5, blue is still 3 out of 5, but green is 0 out of 5 because there's no green stones left. That is the one you removed. Okay, pause if you need to, really think about it. Again, really big idea in probability. Please make sure you understand. All right, on the bottom, we're looking for selecting 1 green and 1 blue in any order. So that means green blue or blue green. So we're going to look for those 2 paths. Green blue path plus the blue green path. So here's the green blue path in red, and in blue we have the blue green path. So probabilities of those, you just multiply 1/6 times 3/5 for the green blue path and 3/6 times 1/5 for the blue green path, and you add those because it's an OR problem. 3 over 30 plus 3 over 30, 6 over 30 equals 1/5. Again, check your work, make sure you are good with that, and let's move on to the photocopier problem. In the photocopier problem, we have this situation where photocopiers fail. Machine A fails 8% of the time, machine B fails 12%. So what's the probability both, it says both will malfunction. So that means A fails, B fails. So you just multiply. Probability of A fail times probability of B fail, and you multiply 0.08 times 0.12. That gives you some value. You have to calculate that. I don't have a calculator, but you do. Go for it. In part B, you're looking for both working effectively. So if A fails 8% of the time, it must succeed or work 92% of the time. So A works, B works would be 0.92 times 0.88. It's just the complement of the failing percent. So 92%, 88%, you multiply those, and again, you're going to get some number which you have to figure out. Bottom problem, make a tree diagram. Probability A works and B fails. Here is the tree diagram. Machine A and machine B. So notice how the first branch in the tree diagram is just showing what happens to machine A. The next branch, 2 branches, or 4, I guess, branches is machine B. You could have done them in any order you want. You could have put machine B first, machine A next. The order of the tree diagram doesn't matter. It just means one thing happening and another thing happening and another thing happening, so the order is not important. So here we have machine A, 0.92 is it works, 0.08 it fails. Machine B, 0.88 works, and 0.12 it fails. And then the same probabilities on the bottom for machine B, because whether machine A works or not doesn't determine how machine B works. So there's no dependence. This is independent. And we're looking for a probability A works, B fails. So you follow the yellow path, A works, B fails, 0.92 times 0.12, and you will get some value. Pause if you need to draw that properly. Next problem is the same photocopier, well, different photocopiers, and now it's dependent, because what happens with copier C determines what happens with copier D. All right, so here's the diagram. Take a close look, make sure you understand what's going on here, but the main thing to note is we have copier D has a different failing number. Look at that branch there, 0.12 if copier C works, but then the failing number for copier D is 0.17 if copier C fails. So in other words, copier D is more likely to fail if copier C fails. And that could be because if copier C fails, more people are using D, so it's going to have more of a chance to fail as well. So anyway, notice the branch, all these numbers have changed because there's dependence here. And the question asks for only one will fail. Actually, 2 branches lead to only one will fail. Only one will fail can be copier D failing or copier C failing. So notice the yellow has highlighted both of these situations. The top yellow, copier C works, but copier D fails. The bottom branches there, copier C fails, but D works. So you follow both paths. You do a OR situation, you figure out the probability of each, then you add those probabilities, and you get your final answer. So make sure you calculate that. And copy it, pause if you need to. I'm going to switch the slide now. Last thing I'll leave you with is scenario A for the people who are firing at a firing range, and you're looking for John and Benita shooting. And I've set up the basic one there to help you get started. It's up to you to figure everything out. I've even put A, C, D, B beside those to represent each path is an answer to each of the 4 problems there, so you can figure that out. All right, do your best with the rest. I know you can do it. You have a strong mathematical mind, and you are becoming a probability expert, so use everything you've been given here to proceed with the homework. You can do it. Good luck.